Hello. Here we will talk about inverted matrices. Let's start with defining what it means. Let's take a square matrix of some size. Its inverse is a matrix of the same size, also square, and what it has to satisfy to be the inverse to A is the following two equations. If we multiply the original matrix with its inverse from the left or from the right, the answer should be the same identity matrix of the same size. And that is to model inverse numbers, inverting numbers, but in numbers we have commutative multiplication. In matrices we don't, so we have to really assume two conditions at the same time. What effectively happens is that one will be enough for matrices, but that comes as a result of some work. When we define inverse matrices, it's better to define them using both conditions because both are true for numbers. So the first point to make about inverse matrices is that they don't have to be there for any A. Not all matrices are square, assuming still, not all square matrices have inverses. That is called being invertible. Easiest example will be a matrix of size 2. Well, already numbers are not all invertible. 0 is we cannot divide by. But in matrices we can have not total zero matrix, but enough zeros in it will make it non-invertible. So for example, this matrix with the first zero row, when we multiply it with anything, then we will always have a zero row in the product, and we won't be able to see the identity matrix. So whatever we multiply it by will always have first two zeros in the row and whatever in the rest. So it is never equal to the identity matrix, which has all its rows non-zero. That is an easiest example, but there are many more. Second point to make is when we do have inverse to a matrix, it is unique. Mathematically, that would be the following implication. Let's assume the opposite, or let's assume that we have two candidates for inverses. So we have one solution of this inverse equations for A called B. So B is going to be A inverse, but then we have another from the two. We should be able to conclude that these two solutions are actually the same. And that conclusion can be made by just doing arithmetic of matrices, playing with these equations. So that conclusion is left as an exercise. It is a formal exercise, arithmetic exercise, but still a good one. The next is that elementary matrices, which we talked about in the previous meeting, are invertible. They do have inverses, and that is because elementary matrices, when we multiply by them from the left, they just do elementary transformations, and we can undo transformations. So multiplication has to be undoable as well. What undoes a transformation is another elementary matrix, which is the inverse. More precisely, just saying what are inverses for each of the types. Addition type, row addition type, inverted by row addition type, which is row subtraction. So instead of adding column J to column I with coefficient C, we subtract it with coefficient C again. Row swap is undone by the same row swap. And then scaling with coefficient C is undone by scaling with coefficient C inverse. C, for that very reason, is to be non-zero. So these are the basic examples of invertible matrices, and actually any invertible matrix is a product of those. For products of invertible matrices is invertible. So if we have two matrices A and B and we multiply them, and if A and B have inverses, then the product will have its inverse. The answer for the inverse is slightly different to what we are accustomed to in numbers. It is the product of inverses, but in the opposite order. So that is the manifestation. That is a manifestation of non-commutativity. Not A inverse times B inverse will be inverse to AB, but this one, again, it's easy to check using the definition that when we multiply AB with this from the left or from the right, we will get the identity. Again, this verification is left as an exercise. And next, we can talk about how to practically find inverses, an algorithm for finding inverses. And this algorithm will be such that it will just work only when we do have the inverse, and it will give us that inverse. So let's start with a square matrix. To find its inverse, we have to enlarge it, extend it by the same size identity matrix. So that is n by n, the same for the identity. The total extended will be n by 2n. It will have twice as many columns, but the original extension is just by columns of the identity matrix. And then what the algorithm asks us to do is, as usual, Gauss elimination, transforming the first half to the best possible reduced row echelon form. And for a square matrix, it shouldn't have 0 rows, just for that very reason. Otherwise, the matrix will be non-invertible. But the invertibility in this algorithm manifests itself in the answer for the reduced row echelon form of A being just the identity. So the pivots are all on the diagonal. There are no zeros on the diagonal, all occupied by pivots. And in the reduced form, it will be nothing but the identity matrix. Then in the second half, what we will see is the inverse. So that is the schematic presentation of the algorithm. Why it is to work is actually easy to see, knowing already that elementary transformations, which we do in this Gauss elimination process, are nothing but multiplying with elementary matrices. So when we transform the first half into the identity, we multiply from the left our matrix with the first elementary transformation, the next, and all whatever we need to do to make it reduced row echelon form, which is going to be the identity. So that is a matrix equation now, and we can now turn it into the answer for the inverse matrix. That is going to be the inverse matrix, because that multiplied by A gives us the identity. So if we do have the inverse, it must be it. And that is automatically computed by the clever algorithm here in the second half, because we do the same elementary transformations throughout. We do the row transformations of the extended matrix, and in the second half of the extended matrix we multiply with the same sequence of elementary matrices, but now the identity matrix. And that will be just that product which multiplied with A gives us the identity, and that is the one of the inverse conditions. So that is again sufficient, because if we do have the inverse, it must be it. As an illustration, let's look at the generic 2 by 2 case. So A is a 2 by 2 matrix, A, B, C, D, and I'm interested in finding the generic answer for its inverse. For just performing this algorithm, let us extend it by the identity matrix of the same size 2 by 2 as we should, and then start doing elimination in the first half to make it to make a reduced row echelon form there. The first step will be eliminating C. Well, I have to assume that A is non-zero to do that, but here let me do this assumption. Assuming that A is non-zero, I can divide by A and multiply by C, and then with this coefficient subtract row 1 from row 2, and that will create 0 here. The first extended row is unchanged, the second is going to be changed. So what is happening in this position, original D changes to BC over A. In this position, I'm subtracting 1 times C over A from 0, so I'm creating negative C over A here, and here I just still have 1. Okay, let's continue. The next step will be just to scale down by this number the second row to make this pivot 1. So I already have my 2 pivots, assuming that A is non-zero and this number is non-zero, and that is already a good thing. So again, doing this assumption, the number which I'm dividing by, or rather multiplying, the inverse of this number will be A over AD minus BC. So that's what I'm scaling row 2 with. Row 1 is not changed in the process. Row 2 turns into 0, 1 in the first half, and the second half will have to be scaled. So first coefficient is going to be negative C over AD minus BC, and this entry is going to be A over AD minus BC, and above I'll have 0, 1, and 0. Continuing with elimination, that is already a row echelon form, assuming that A is non-zero, which we did assume, and then we just continue with reducing this row echelon form, namely getting rid of the number B here. That can be done by, again, row subtraction. Row 1 minus B times row 2 will do it for us. Row 2 is not changing, I'm copying it as it is. So that is C, not A, sorry. Then multiplying it by B and subtracting from the above, I will have AB with minus sign over AD minus BC, the same denominator persisting everywhere. So here I have 1 minus this times negative B. So 1 plus this times B. 1 plus BC over AD minus BC. And I'll create the common denominator straight away. And that will be AD minus BC plus BC. So what will be left is AD over the denominator. And that is with the left side being A and 0. So the final step I need to make is to scale the first row by A. That will make the left half just the expected identity matrix as in the algorithm, and on the right I will see my inverse. Dividing by A throughout, I will have D over AD minus BC, negative B over AD minus BC, negative C over AD minus BC, A over AD minus BC. This denominator AD minus BC is one and the same for all matrix entries, so I can write the answer for the inverse as this scalar multiple in front, and what is left is something which will look much nicer, D minus B minus CA. So just a certain rearrangement with some signs changed of matrix entries up to this prefactor. And that is the answer which we got assuming that first A is non-zero and that this number is non-zero. Well, what happens is that assumption that A is non-zero is actually redundant. We don't need to make it. What is crucial is that this number is non-zero, so the answer makes sense. But in the answer, even if A is zero, this will still work. It can be proved, can be verified by direct multiplication. When we multiply two matrices, we will get the identity matrix. Doesn't matter from the left or from the right. So that will be just the actual proof that the formula here works always as long as the denominator is non-zero. That is how we can invert 2 by 2 matrices, just by doing this rearrangement and dividing by what is going to be called the determinant. So that is the only example we will do here. More examples will come later. What I'm going to finish this story with is, well, straight away we assumed that the matrix is square for it to be invertible, for it to have inverse. These equations make sense even if the matrix is not square. So why not to try and find inverses for non-square matrices? The point is that there are no solutions for the inverses if matrix is non-square. This is going to be important. This is not just of academic value. This is going to be actually of practical meaning. Will have practical meaning for us later. So let's make again a precise statement that let's imagine that we have a matrix of some random size m by n, and then another matrix which is its inverse of the opposite size. So the number of rows is the same as number of columns, so that we can multiply A by B and B by A. This time the answers will be of different size, so that will be of size m by m. Let's assume that this is identity of size m. This answer again is going to be a square. This is n by m multiplied with m by n matrix will be of size n by n. Let's again assume that this is the identity matrix of size n. So what we're going to see is that inevitably under these conditions m and n will have to be the same, so we're back to where we started with square matrices. And the argument will be again involving elementary matrices, involving what we know about matrices, namely Gauss elimination outcomes. So let's assume that these are not square. It doesn't matter what is larger and what is smaller, but for concreteness, let's assume that m is less than n. then B is going to be of size n by m. It will have more rows than columns. And then when we do Gauss transformations, eliminating as much as we can, creating a row echelon form, we will inevitably create a row of zeros, because we won't be able to have pivots going all the way down to the corner. Pivots will run out of space because we have more rows than columns. So we're going to have a reduced, just a row echelon form, but it's going to be, with inevitability, it is going to have a row full of zeros. And since we're doing elementary transformations, this new matrix is a product of the original one with elementary matrices, again, some matrix E, E prime, whatever it takes to make this row echelon form. So let's call this matrix C. As a product of elementary matrices, they are all square of size n by n. So this is our product of elementary matrices. Each of them is n by n. The product will be, again, square of n by n. Because products of invertible matrices are invertible, and because elementary matrices are invertible, C is invertible. And so what we have is the product of that invertible C with our B, giving us a matrix with the last row being full of zeros. So let's use it to make a contradiction with the assumption here. Let's look at this equation, which we have as given, and multiply it with C from the left. C, the product with B, is going to be this B prime. And to make a contradiction seem easier, let's multiply with C inverse, because it is invertible, from the right. So that way we'll create identity matrix in here. So now let's look what happens. In this matrix, we have the last row being all zeros. Whatever happens in this matrix, we don't care. Because whatever happens doesn't matter. We are going to have the last row of the product being all zeros again. When we compute entries in this, we take the row, we multiply with a column, and we take the sum of products. And it will always be zero. So that is not going to be equal to the row of the identity matrix, the last one, which has all zeros but one at the very end. Just because of that, rows are different. This answer will never be possible to make equal to the identity matrix. So we have contradiction. Contradiction means that what we assumed is impossible. And that's how we can conclude that sizes will have to be square. That's it for now. See you later.